Hello everyone. So in the last lecture we have discussed about the elastic wave propagation. We discussed elastic wave propagation in a finite body like cylindrical bar when we impact a cylindrical bar with a cylindrical projectile. Also we discussed about the elastic wave propagation for a unbounded media. We discussed about longitudinal wave velocity, shear wave velocity and Rayleigh wave velocity, which is surface wave velocity. We also discussed about some additional considerations we need to take care of while analyzing the split Hopkinson pressure bar experiment. So now we will talk about the plastic wave in this lecture. So when stress pulse amplitude exceeds the elastic limit. So when the stress pulse amplitude exceeds the elastic limit, the pulse will decompose to elastic wave and plastic wave. So we know that when a material is stretched beyond a limit, that is elastic limit, the plastic deformation happens to the material. So similarly in this case, so when we have a dynamic loading, the stress pulse amplitude, if it exceeds the elastic limit, so then this wave will be decomposed into elastic component and the plastic component. So here we will discuss about the three classes of plastic waves. Three plastic waves, that is, we can call three classes of plastic waves, and the first one is plastic waves in rods or wires or bars. So in this case we have, let us say one example is we have a rigid target and we have a cylindrical rod, or we can draw it a little longer. Let us say the cylindrical rod is hitting the rigid target, and this is a case of uniaxial stress. If the stress pulse amplitude is sufficiently high, then plastic deformation will happen and plastic wave will propagate through it. Then the second one is plastic waves in semi-infinite bodies. So this is the case when the lateral dimension of that, suppose we are talking about this rod, are infinite, so that will lead to actually lateral strain 0, lateral strain just 0, and which is a case of uniaxial strain. So the earlier case we had uniaxial stress and here it is uniaxial strain, and this will lead to a very sharp front of wave, and that is called a shock wave. So when it is a uniaxial strain condition, and that is the wave front will be very sharp, and that is called a shock wave, and the third case is plastic shear waves shear wave, torsional waves in bars, and shear waves in semi-infinite bodies, these can generate plastic deformation or plastic waves. This can lead to plastic waves if that amplitude is sufficiently high. Stress amplitude is high, that should be higher than the elastic limit. So, we will discuss a few cases of plastic deformation, as we know that material strength is dependent on strain and strain rate. So, we know material strength depends on strain and strain rate. Now, in the simplest case, we call it a bilinear elastoplastic, where we have a straight line, in this case an elastic portion, and then another straight line with different slope as a plastic portion. U1 the stiffness, elastic stiffness, this is the slope is different here for the plastic portion. So, this is we call as a bilinear elastoplastic behavior. These all are stress strain curves. We will show different stress strength, and there can be another model which is we call power law work hardening. So, the first one is the simplest, very simplified case, but in reality we can get these type of stress strain relationship, which is we call power law work hardening. Why we called it as a power law work hardening? Because this work hardening portion, the rate portion, we can express the stresses, the flow stress, sigma equal to sigma naught k epsilon to the power n. So, this sigma naught is the yield strength, and k and n are the two materials constant, n is we know as a work hardening or strain hardening exponent. Some material can be strain rate dependent. So, in this case, third case, we will strain rate dependent flow stress. So, what happens here is, let us say you have a flow stress behavior like this, and when you, this is let us say at epsilon dot, and then if we increase it, the strain rate, it will look like this, and if we increase the strain rate more, so let us say this, the stress strain curve look like this. So, here strain rates are in increasing order. So, this is strain rate dependent flow stress. So, the constitutive equations we can write in this form: k epsilon to the power m epsilon dot to the power m. So, this strain rate term, and then this m will be in between 0 to 1. Similarly, in other case, I did not mention here, so n is smaller than 1. So, m is generally referred as strain rate sensitivity, the strain rate sensitivity. So, in the fourth case we will see that it depends on the material behavior depends on the strain rate history. So, dependence of flow stress on strain rate history. So, here what we will show is, let us say this is the material behavior, and that is at, let us say, strain rate epsilon dot, and if we, let us say, increase the strain rate at strain epsilon 1, then the material will increase, will show increase in the flow stress, and what we did here is at strain epsilon 1 we increase the strain rate from epsilon dot 1 to epsilon dot 2. So, now the material behavior is something like this, but in case if someone else wants to increase the strain rate at a lower strain epsilon naught, then what will happen is, so with the same strain rate, actually it should be like this from our earlier predictions, but actually it goes like this. So, what happen here is, let us say this is our flow stress. If you see at a point corresponding to strain epsilon 1, here the flow stress is sigma 1, here the flow stress is sigma 2, and here the flow stress is sigma 3. So, what we did first, what we did is we have the stress strain curve, and at strain epsilon 1, so we increase the strain rate from epsilon dot 1 to epsilon dot 2. This is at strain epsilon 1, and then what we got this curve, and in the second case what we did is we changed the strain rate epsilon dot 1 to epsilon dot 2 at a lower strain epsilon naught. So, what happens in this case, the stress curve will go up in this portion and it will not follow the same slope as this. So, it will have a higher slope. So, that means the work hardening is higher, So, flow stress will depend on the strain rate history. That means when we increase the strain rate, whether we increase at a strain epsilon 1 or whether we increase at a strain epsilon naught, that will decide what will be the work hardening, and we can see that slopes of these curves are different. So, this slope is lower, this another one the slope will be higher. So, this should be flat and this slope should be higher. So, we will discuss about the plastic waves now, and so we are discussing actually the plastic waves, and the treatment of plastic waves are complicated, complex because of strain rate effects and strain rate history effects. Plastic wave treatment is more complex than the elastic wave due to, first thing is, strain rate effects that we have just discussed, strain rate effects, and effects of strain rate history. Strain rate history, what we have just discussed. So, in 1950, von Karman and Dewey proposed the plastic wave propagation equation. Propagation equation, which is the velocity can be given by d sigma d epsilon divided by mass density square root of the whole thing. So this is the velocity of plastic wave. Velocity of plastic wave, and is only at fixed strain epsilon, because the d sigma by d epsilon, which is d sigma by d epsilon, which is the slope of the plastic region of the stress strain curve, region of the stress strain curve, and the slope we define it only at a fixed strain. So that is why the velocity of plastic wave, this is defined at fixed strain. Now, if we compare this plastic wave velocity with our elastic wave velocity, whatever we discussed earlier in earlier lectures, so that we know the elastic wave velocity is square root of the ratio of E by rho, and so even if we see this both the equation V elastic and V plastic, which is d sigma d epsilon by rho. So, here in the elastic region, so d sigma d epsilon is E. So, if we draw the curve, stress strain curve, it will look like this is the elastic portion, and then there will be yield, and with strain hardening it will go like this. So, first portion in the elastic region, the slope E equal to d sigma d epsilon, let us say 0 at sigma naught actually. So, then we will have another slope, let us say at sigma equal to 1, which is in the plastic region, and d sigma d epsilon at 1, and then sigma 2 slope here is less, d sigma d epsilon at 2. So, we can see that for elastic region this is the slope, and for the plastic region we got two slopes for sigma 1 and sigma 2. The first slope is higher than the other slope. So, and also what we can see from elastic and plastic is d sigma d epsilon for elastic, which is this one, is higher than d sigma d epsilon plastic. So both of these are smaller than the elastic slope. So that means velocity of elastic wave is higher than the velocity of plastic wave. So that is an important conclusion from here. And also V decreases in the plastic region with decreasing, or we can just write Vp decreases with decreasing work hardening. V2 is smaller than V1. So V1 corresponds to this and V2 corresponds to that. So the slope of V2 is less, and that means V2 is smaller than V1. We will see that how the velocity will look like. We will plot it with sigma versus x. So the velocity, which is okay, we will start from the bottom. So here the velocity is high and constant, and then it will something like this. So here V2, as you can see, the V1 sorry, we should write this one also for at sigma naught, at sigma 1 and sigma 2. So this is V1, and then this is constant, this is V naught in the elastic region, and this is, let us say, at time equal to t1, and at a later time, if we take this with higher strain. So what will happen here is so this will be more variation here. So this is V2, V1, and this is V naught. So we can see that this is how the plastic wave travels. We can see the different velocities. So basically we will discuss here three types of plastic waves: the plastic waves of uniaxial stress, and plastic waves of uniaxial strain, and plastic waves of combined stress. So that we have even discussed in a few slides earlier. So for plastic wave of uniaxial strain, which that means lateral strain is 0, strain 0, or lateral dimension is very like it's infinite lateral dimension. So this will be this is called shock wave if amplitude is sufficiently high, and for plastic wave of combined stress, so we have like plastic shear wave, plus plastic longitudinal wave. Basically in the upper two cases, case number 1 and 2, we mostly focused on longitudinal wave, but in this case we have shear wave as well, and that means let us say torsional waves in a bar and shear wave in a semi-infinite body can also generate plastic waves. So, first we will talk about of uniaxial stress, where the lateral dimension is very small. That means, suppose if we are talking about a bar, the bar radius is very small, and there are, you can write that the bar diameter is very small, bar or wire diameter small. And so there are three theories of plastic waves generally we follow, and so this is this three theories of plastic waves which are initially proposed by first one is von Karman and Duez, and then Taylor and the third one is Rahmatulin. So, they are these three are independently developed theories, and then we will mostly discuss on the first one, which is a paper in the published in the year of 1950. So, we will discuss here. Oh, sorry, this the capital lambda is not correct, because that is the stress amplitude. So, the capital lambda we use for wavelength. So, basically the shock wave is for the plastic wave, that means if the amplitude is sufficiently high. So, plastic waves of uniaxial stress. So, what we will discuss here is von Karman and Duez theory, and then we know two frames of reference which probably you have studied in your undergraduate courses, probably in fluid mechanics. So, we have two frames of references for these type of disturbance propagation problem. Even in fluid mechanics, for fluid displacement problems, you have encountered these two frames, frame of reference. At least you read about these differences between these two frames of references. So, this type of disturbance propagation problem, like our stress wave propagation, so for this type of propagation problem, as you know, the first one is material or Lagrangian coordinate, and the second one is spatial or Eulerian coordinate. So, what happens in the first case? First case is one considers a particle of the material and observe the change of position, and then observe the change in position of that particle, change in position of the particle with time. In the other case, one considers a certain region or space, region in space actually, space and observes the flow of material in that point, or in that point of space, or in that region. So it's basically von Karman and Dewey's. For material and Lagrangian coordinate, they used the von Karman and Dewey's, and also Rachmaninoff. They use the material. He used the material and Lagrangian coordinate, and on the other hand, the special or Eulerian coordinate, Taylor used it for his theory of plastic wave. Now we can try to understand these two coordinates like this. I am sure that you have already studied in your undergraduate about these two frame of reference. So a simple example is, I will show you here. Let us assume a stadium of 400 meter track, 400 meter track, and so there are, let us say, a 5 kilometer or 10 kilometer race is happening in that track, and you are the observer, this is you. So this is the observer O, let us say, and let us say out of those the runners, let us say 20 runners are running here, and one of them is your friend. So what will happen, in that case you will see your friend only where he is, whether he is in this position or this position or this position. So you will focus on your friend because you know only one person. So that is why it is like you consider the particle, this is actually Lagrangian coordinate system, and let us say you are the observer 1, and then another person who is the observer 2 in the same location, let us say observer 2 who does not know any of the runners or those athletes. So what will happen is he will focus only on the small region, let us say this region, he will only focus only this region, and he will see all the people who are crossing by that area. So that is like a consider the region in the space, and so observer 2, if we consider that is a Eulerian frame of reference, and observer 1 who is like you observing only your friend, not the other runners. So that is Lagrangian coordinate or Lagrangian frame of references. So any property, let us say P is a property, and that varies, P is a property that varies with time t, and then special coordinate x. So that these coordinates we will write at x, and the material coordinate we will write is as small x, this small x, this is capital X. So it varies with small x and capital X. So P can be either expressed as a function of small xt, or P can be expressed as function of capital X and t. So that is the two frames of references. So we will talk about the experiment, that problem that von Karman and Dewey's they used in 1950. So that is probably the simplest problem of plastic wave propagation. So this is from the reference von Karman, if you can see the lower bottom corner, von Karman and Dewey's in 1950. So this is the simplest problem of plastic wave propagation. So this is the initial position. We will focus on the initial position. So this is a infinite thin wire, semi-infinite thin wire. This is, let us say, annealed copper, made of annealed copper. It's ductile material, very ductile material. So we have some weight here, W. This is weight, and so this one rigid plate attached to the wire, and then this weight will be dropped, and a rubber, this is a rubber band, will accelerate the weight, the falling of the weight, accelerate the weight, and then the weight will impact on that rigid plate, thereby deforming the wire. So this will be plastic deformation of the wire. Actually we are focused on the wire now. So this thin wire will be plastically deformed, when the weight will impact on the plate, and the allowable deformation here is D. You can see that this is one anvil, and then you can vary this distance. So what will happen when the weight will impact here, let us say this is small d, that the portion of the wire from the weight, initial position of the weight to the rigid plate. So now the weight will travel a distance d, small d, and now the capital D is the allowable deformation, and the total, you can say the total wire extension. This is total wire extension, and then weight W is sufficient enough not to be deaccelerated significantly when the plastic deformation is happening. So when the plastic deformation is happening, if the weight is low, then there may be some deacceleration, but that is why the weight is intelligently chosen, so that it will not have much deacceleration. So now we will see the position after impact. This is the position after impact. Now if we see that this plate is impacted by these weights, and then by these weights and generating a velocity downward v1. So if we consider this dotted line, this initial position of the plate as x equal to 0, and then this is a point on the wire it as x equal to x, that means this distance is x. So this displacement of this point in the downward direction is u. We should focus on this, that this wave will travel on the upward direction. This is the wave propagation. So that we should understand this is a tensile wave. So wave propagation is upward, but material displacement is downward. So the sense is opposite here. So this is wave propagation is upward and material displacement is downward. Here, so we should also mention that in these experiments, so here we should mention that in these experiment there some equidistance mark is kept on this wire, if you see at this, so that to get the displacement here. So here we have two so we have this point is displaced by a distance u, and the final at the current position it is at this location. So so we are considering a particle at x at a time t. The particle is, let us say, displaced by u. So at position x, that consider the particle and which is at x and time t, and displacement is u. So we will apply the Newton's second law here. Newton's second law for that particle. So df equal to dm second partial of with u with respect to t, which is the acceleration term, and then dm is the mass of that small element particle, which can be written as the initial density rho naught into the volume of this the small element, and with again second partial of u with respect to t, and then again we can write initial mass density into initial area, the cross sectional area, and then dx is the thickness of the small element. So if we are taking the wire, so this is the dx, and cross sectional area, this is initial is a naught, and we have rho naught is the initial density, and this will be equal to, as we know, a naught d sigma, area multiplied by the stress acting on it. So that will give us d sigma by dx is equal to rho naught this. So now we want to have a wave equation which is so this is the relation we got. Now what we are doing is we want to derive the wave equation from here for the plastic wave propagation equation. For that we want to get the wave equation in a form which is similar to the elastic wave propagation equation. So for that we know that sigma and epsilon in the plastic deformation region has a 1-to-1 relation, 1-to-1 relationship in loading. So in unloading it can be different. In unloading this is irreversible, that we are not going to discuss it now, but that may not be a 1-to-1 relationship, and this is in the for plastic deformation, plastic range, plastic, I will write plastic region. So, this has one-to-one relationship. For one-to-one relationship, what we can write d sigma dx is equal to d sigma by d epsilon. So, we are writing d not partial derivative because it is one-to-one relationship. So, and partial of strain with respect to x. So, that is strain is a multivariable function, and then so we can write the above equation as rho naught second partial of u with respect to t equal to d sigma d epsilon partial of strain with respect to x, and then we know that epsilon is equal to du by dx. So, from that what we can do is d sigma by d epsilon divided by rho naught. So, the left hand side will be the left hand side will be something like this, and this will end up with a like equation like this. So, this is plastic wave equation. So, this is plastic wave equation. So, if we compare this equation, so if we compare the equation in the previous slide, so with the elastic wave equation, like the elastic wave equation for a finite body, so we had it like this. So, this is elastic wave equation, elastic. So, if we compare with this, so our plastic wave velocity is Vp, which is d sigma d epsilon by rho naught, the entire whole thing is square root, and that is at constant strain or fixed strain epsilon, because d sigma by d epsilon we define at a constant strain. And if in the again if we see again in the elastic range, in elastic region, so as we know the slope of the curve is E. So, what we can do is, for if we substitute that, so our V will be equal to, not V will be equal to E by rho naught. So, which is exactly the same as the elastic wave velocity. So, what we are showing it here is, if you take the plastic wave velocity and then substitute this d sigma by d epsilon, which is the slope in the plastic region of the stress strain curve. If we know that in elastic region the slope of the curve is the E, and that is Young's modulus, and then after substituting we get E by rho naught, which is exactly the same what we got earlier for elastic wave propagation. By the way, this elastic wave propagation is for a finite body, and for that is for basically when the bar of small diameter, rod or bar of small diameter, these equations are valid. Let us say for r divided by wavelength is 0.1, and also so this is different than the elastic wave velocity in unbounded media, which is let us say for V unbounded, V elastic for unbounded is equal to V elastic of the finite body, or this whatever we got for, let us say for rod, that will be 1.16 times of this. So, 1.16 times of for the elastic wave propagation velocity in a rod will be equal to the wave velocity, elastic wave velocity in unbounded medium. So, that is all for today. So, we will continue in the next lecture. Thank you.